For the first example of how to apply position, velocity, and acceleration graphs to real situations, let's imagine here having a ramp. We'll have it slant downwards that direction. We'll put a ball at the top, and the ball will roll down the hill or down the ramp till it gets to this point. We're only going to go that far. We're not going to worry about the ball rolling off the end or anything else. Let's label the left end of the ramp 0. Let's label the right end of the ramp 50. This would be like a distance, so it's going from 50 down to 0. It's going left or backwards, so I can label that here as well, that the velocity is going to be that direction towards the left. I'm going to ignore uphill and downhill for the moment. When I talk of positive, negative, I only mean left or right. The initial velocity of this ball is 0. So we're imagining putting it on a ramp, putting my finger on the ball perhaps, setting it down the ramp, holding it still, and then lifting my finger up quickly so as not to joggle the ball at all, and having it roll down the ramp all on its own. The first way, I want to draw position, velocity, and acceleration graphs. I find that it's easiest perhaps to start with acceleration. I know the ball's going to roll downhill. Acceleration has to be down the hill or to the left. And so it's very helpful to label that so that you know which direction the acceleration is going to be. Recall that acceleration means change of velocity. So right here at this moment, when I first lift my finger up, the ball is not moving. It very quickly begins moving. That's acceleration. It's moving differently than it was before. As the acceleration points left, I'm going to label it negative. Now, if I were to draw an acceleration graph, I know that for the time period I'm talking about, the ball stays on the ramp, nothing changes. The ball is just going to roll down the ramp, and so for that entire time, the acceleration of the ball is going to be a negative acceleration. However much time that is to cover this 50 units of distance, the acceleration is going to stay negative the whole time. The ball is not going to suddenly stop rolling down the hill and do something else strange. It's just going to roll down the hill. The velocity graph that we get from that would show that the ball is not moving at the initial place, at its initial moment, and then begins to roll to the left also. We've labeled left as negative, so we're going to decide that velocity is negative also. So for the time that the ball is rolling down the hill, its velocity is negative. And remember from the patterns of the graph that if acceleration is negative, the velocity line has to slant downwards or with a negative slope. And so that would be the velocity graph that we would get. The position graph of this ball, it's going to stay between 50 and 0, so I only need to draw the first quadrant here. We'll label this as 50, we'll label this as 0. I know that when time is equal to 0, the ball starts there at the top of the ramp. And so I will draw a dot on the diagram to represent where the ball starts at 50. I know that by the time it gets to the bottom of the ramp, whatever amount of time that is, it has to be down there at that location. Now from there I have several choices of how to draw the shape. Okay, it has to be a parabola, but the question is what kind of parabola. From the patterns, remember that if acceleration is negative, then it has to be a bottom opening parabola or a concave down parabola. If the initial velocity is 0, that means I'm going to be starting with a flat part of the parabola and then having it get steeper. So it would look kind of like this perhaps. And that's supposed to be a parabola with a constant curve all the way down to the bottom.